Hello Aero 590, we are Team 1, and today we will be discussing the risks of automation in commercial aviation. Aircraft automation, which in some manner has existed since the very first airplanes ever flew, is implemented with the goal of reducing pilot workload, improving performance efficiency, and increasing the overall safety and reliability of the aircraft. On paper, this appears to have succeeded, as accidents due to mechanical failures continue to decrease and pilot workloads have also been significantly reduced. However, as technology evolves, so too does the role of pilots, who today may more resemble system managers as opposed to operators. While requiring less complex technical expertise in hand flying, this calls for increased skills in monitoring and intervening with automated systems. Despite a widespread adoption of automation with the goal to improve aircraft safety, accidents that could be attributed at least in part to automation have still persisted. Therefore, we will examine several cases of automation-related aircraft accidents, categorizing them by safety risks and error mechanisms to find common causes and connections among these accidents. Using this information, we will evaluate any risks or shortcomings with aircraft automation, ultimately looking to use this as a basis to guide recommendations to mitigate any such risks and reduce automation-related accidents in the future.
Here's a brief overview of how our presentation is organized. We just discussed the issue of safety regarding automation in commercial aviation and the overall problem that we researched. Next, we'll give a brief overview of some of the main automation features in commercial aviation. Then, we'll present our methodologies for classifying the accidents that we researched. We'll highlight a few of these selected accidents and show how our classifications are applied to them. Then, we'll show some of our findings from all the accident studies that we did. And finally, we'll close with our conclusions and recommendations on how safety with automation can be improved.
Before we get into looking at actual accidents, we researched the current state of automation in airplanes to better understand how these systems can contribute to accidents. We grouped automation into three categories: control automation, information automation, and management automation. Control automation assists pilots in controlling the aircraft through maneuvers necessary for their safe performance. The main system associated with control automation are auto throttle, the fly-by-wire system, and the nav-aid system. Through using these control automation systems, pilots can decrease their workload, limit physical exertion, and ensure that they don't push the aircraft past its design limits. Information automation systems automate the flow of information used by the pilots during aircraft operation. The information is gathered and displayed on the primary flight displays, which can be seen in the cockpit image. The displays show navigational information, engine information, important subsystem information, as well as alerts and warnings. Information automation improves the flight crew's situational awareness and helps the pilots make informed decisions. Management automation serves to manage the overall function of all connected systems within the aircraft. The Flight Management System, or FMS, is the metaphorical brain of the aircraft, as it takes inputs from all the aircraft systems and interprets those inputs to generate commands. Those commands are then sent to the appropriate control automation systems or displayed as feedback for the pilots. As shown in the figure, the FMS gathers navigational data, state data, and system data to make informed commands with only the pilots having override capabilities. Modern FMS systems utilize two flight management computers for increased redundancy. After better understanding current automation technologies, we sought to define our research methodology. Our research methodology involves selecting 20 commercial aviation accidents and/or incidents that occurred within the last 30 years. We summarized the cases and classified them based upon their level of interaction, their error mechanism, and their preventability, which we'll explain on the next slides. The data was then compiled into a table so that the trends could be analyzed. Finally, we composed our conclusions based upon the trends shown within the data and made recommendations for the future design and implementation of aircraft automation.
There are several ways in which pilots interact with automated systems over the course of a given flight. We wanted to identify what the level of interaction was when an accident originated from, to identify where improvements can best be made. The first level is the planning stage, which is when pilots generate the flight plan. An error at this stage could be the pilot plan is outside of the capabilities of automation, such as trying to use ILS when ILS is not enabled on a runway, as was the case with Korean Air Flight 801. The second stage is teaching, which is the process of pilots entering information into the automation manually. An error in this stage could be entering the incorrect navigational information, such as with American Airlines Flight 965. In the monitoring stage, pilots are focused on ensuring automation is functioning as anticipated and desired. Errors can arise if pilots are not adequately monitoring the automation, such as with Asiana Flight 214, when pilots were not aware of a mode change, which caused a decrease in speed. Intervening is when pilots adjust automation from the current state. An accident may occur here if the intervention exacerbates the situation, from pilots trying incorrectly to adjust automation, or from their own manual actions in place of designed automation, such as with Air France Flight 447, when pilots caused a stall after manually taking control of the airplane. Finally, the design level originates beyond the pilots at the manufacturer or with software engineers. An example of an accident at the design level is Tarim Flight 371, when an autothrottle failure caused an accident. These levels of interaction are also organized such that the role of automation in contributing to an accident tends to increase as we go down from the planning level, which is almost entirely human-centered, to the design level, which is almost entirely automation-focused.
In addition to describing the means of interactivity between pilots and automation, we can also characterize accidents by their error mechanisms. These describe the breakdown of functionality in the operator, automation, or both, and help identify specific lower-level causes of an accident. We will start with those focused on the operator, with human-initiated errors. These describe pilot actions which deviate from typical actions for a given flight configuration, excluding those due to mode error, which we'll discuss shortly. This type of error, which may also be simply called pilot error, describes actions initiated or exacerbated by the operator which resulted in an accident. One example is Korean Airlines Flight 801, which continued an ILS approach despite being informed of a non-functional ILS beacon, resulting in the aircraft straying off course and crashing into terrain. The second mechanism, mode error, is a specific kind of human error that involves a lack of awareness of the current state of automation or the functionality in its current mode. In other words, the pilot believes that the current state of automation is something that it is not, and may attempt to perform an action not available in the current flight mode. Failures of this type often involve inputting information in the incorrect mode, such as with Air and Tear Flight 148, where the pilots intended to input a flight path angle but instead inputted a vertical speed, because they did not realize the vertical navigation mode was set to vertical speed, not flight path angle. While this is a type of human error, it is its own category in our study because of its prevalence in automation-related accidents, as we found. The last error mechanism is a failure or malfunction of the automation itself. These may be design flaws or errors of implementation or operation, which manifest in causal factors leading to an accident. Two examples are the Boeing 737 MAX accidents, where the automatic trim system overrode pilot nose-up commands, resulting in 2 fatal crashes.
We also define 4 levels of preventability of an accident. The first one is highly preventable, which is a case where there's no malfunction of automation system and the main cause of the accident is simple human error. The next level is possibly preventable. For this level, pilots have the ability to take collective actions even though deviations or error were caused by outside factors. Likely to occur is a case where there is at least one way to avoid the accident, but that's not something the pilots were expected to do or received regular training for. Therefore, the possibility of survival is quite low. The final level is accident imminent. For this level, the cause of the accident is faulty automation system or system malfunction, and the pilots have no way to fix it. This is a list of 20 accident cases that we studied for this project. From this list, we picked 3 example cases which we will discuss in detail in the following slide.
One accident we looked at was Asiana Flight 214. This was a Boeing 777, which departed from South Korea for San Francisco. On the approach into San Francisco, the pilots were cleared for a visual landing, since the ILS system was down on the runway. The pilot in control began to slow the airplane, since it was coming in above the glide path. At some point, the flight mode was changed to flight level change mode, which meant that the autothrottle no longer controlled the airspeed. But the pilots were not aware of this change. The crew lost focus on the airspeed until they noticed they were coming in well below the glide path and too slow since the autothrottle was no longer maintaining the speed that they had thought. At the last moment, the pilot attempted to go around, but it was too late. The plane struck a seawall and crashed onto the runway. Since the pilots failed to pay attention to the airspeed and activity of the autothrottle on the approach, this accident is an example of a monitoring error. Its error mechanisms are both human-initiated error and mode error, because the pilots were primarily responsible for the accident, and they had lost awareness of the flight mode, or they did not have knowledge of how the flight level change mode worked with the autothrottle. Finally, we determined that this accident should have a preventability rating of 2, because there was a high degree of human error and negligence involved, which meant that the accident very easily could have been prevented. But the NTSB did make some recommendations for Boeing to improve the descriptions of their automated systems, especially the autothrottle, in the documentation, and to try to make the systems less complicated to avoid confusion in the future.
Another accident studied was the crash of the first ever Airbus A320 passenger flight on June 26, 1988. Air France Flight 296 planned to do a slow pass at an air show before performing a sightseeing tour for 130 passengers on board. The intended flight path was a low-speed pass at 100 feet at maximum angle of attack along the airport runway. During the flight to the airshow airport, the airport was not in the A320's flight management computer, and the target runway was changed at the last minute, causing the pilots to be delayed in making their pass. As a result, they descended at a much slower airspeed and faster descent rate to accommodate for the new runway, causing the actual pass to be about 60 to 70 feet lower than intended. Upon needing to climb out, the pilots applied maximum thrust and pulled back, but the fly-by-wire stall prevention system overrode this command, causing the aircraft to continue into the trees, resulting in a crash and the loss of 3 lives. This crash was infamously caught on camera, which we will show now. Because this involved an intentional flight configuration outside normal safe envelopes, this is a planning error. It is worth noting that while ultimately it was the fly-by-wire system that prevented the pilots from recovering and climbing out of their maneuver, it was the pilots that placed themselves into this hazardous situation well outside normal operations. Therefore, we identify both automation and human factors as accident mechanisms in this instance, and it should be noted that this aspect of the accident's cause is still disputed by the pilots and investigators involved. Lastly, because this involved an improperly flown maneuver, it could have been prevented with correct procedures, better planning, or simply not carrying passengers on such a relatively experimental flight anyway, resulting in a rating of 1.
The third accident we studied was Ryanair Flight 610. This was the first of the 2 infamous accidents involving Boeing 737 MAX. The aircraft took off from the airport in Jakarta, Indonesia on October 29, 2018, and about 13 minutes after takeoff, it entered the nosedive and crashed into Java Sea, killing 189 people on board. The leading investigation revealed that the cause of the accident was the faulty angle of attack sensor and the maneuvering characteristic augmentation system, or MCAS, which was installed on new Boeing 737 MAX to compensate for its pitching up moment characteristic due to a rush in new engines. During the flight, the incorrect angle of attack data caused the MCAS to activate and pitch down the aircraft while overriding the pilot's nose-up input, and the pilot did not have enough information of how to deactivate the MCAS. Since the primary cause of this accident was the inherent design flaw of MCAS, we determined that the interaction level of this accident is design and the error mechanism is automation failure. Because the pilot had not received any training for the MCAS deactivation and nothing about MCAS was mentioned in the flight manual, there is little that pilot could do to prevent the accident, which makes the preventability of this accident to be 4. Here is a table showing the classification for all 20 accident cases we analyzed. As you can see, teaching is strongly tied to more error, which makes sense because pilots' misunderstanding of automation mode is most likely the result they incorrectly configured automation during the teaching phase. Similarly, automation failure most likely happened during the system design phase, as it is usually a result of faulty system design. In terms of overall trend for the level of interaction, the teaching and intervention had the highest number, followed by planning and system design. We also found the monitoring is relatively minor compared to other interaction levels. For the error mechanisms, all 3 types of error are almost equally distributed, and therefore we could not identify which one is more prevalent error mechanism over the other. Rather, we determined that approaching those 3 error mechanisms comprehensively would be effective to improve the automation safety. This table shows the summary of the affected automation system for the accident we studied. As you can see, control is the automation type that was affected for most of the accident, which makes sense as the major purpose of the automation in aircraft is to reduce the pilot's workload by replacing their aircraft control task with the automated controls. That also explains why autopilot, autothrottle, and the flight control account for the most of the system involved. We also found that the alerting and warning system and flight management system are minor in terms of subsystem directly related to the accident. And as with the case of Aeroflot Flight 411 and American Airlines Flight 965, those systems themselves usually do not pose a significant hazard in terms of automation, and the risk can be easily mitigated by proper intervention by pilots or the design change of other parts connected to those systems. We also developed the Human Factor Analysis and Classification System, or HFACS, for 3 error mechanisms as the means to identify the common factors involving those 3 errors and find the potential solution to prevent them in the future. This slide shows the organizational influence and supervision level of HFACS. In context of the aircraft automation, we found that there is a general trend of rapid automation in the aviation field, but at the same time, there is a discussion on whether the automation or human pilot should be prioritized. In addition, there is a shift of focus of flight training from manual control to the use of automated system, and due to the increased amount of automation, it makes it hard for the airlines and their pilots to know and understand everything regarding newly introduced automation system of the aircraft. For the supervision, in addition to conventional errors such as unsafe flight planning and failed crew resource management, errors specific to the automation such as lack of monitoring, inappropriate use of automation, and the negligence of erroneous automation systems are audited. As we observe from these HVACs, we know that automation error can be mitigated even from this high organization level by appropriately teaching the crew how to safely use the automated system, combined with the pre-existing aviation safety measures such as safe flight planning and training. This is another half-part of the HVAC showing more direct factors. For preconditions, automated system can take away the situational awareness of the pilots if they are not properly trained for the system or do not have enough knowledge of how to use them. This can be devastating, particularly when the unusual flight conditions such as bad weather or inoperative airport equipment exist, or the automated system itself malfunctions. Additionally, we also found that inadvertent activation of automation happens when there is a poor cockpit user interface design and the pilot fails to deactivate it because they could not realize the mode change. These above factors eventually lead to the unsafe acts of mode error, automation failure, or human-initiated error.
Using the insights gained from the analysis of the 20 accident cases, we formulated our conclusion. We recognize that airplanes will only continue to become more automated, therefore ensuring their safety is vital to the viability of the commercial aviation industry. We determined that all air mechanisms were equally likely to be present in an automation accident. We also concluded that teaching and intervention were the most prevalent levels of interaction. We found that automation is rarely the sole factor involved and that the lack of familiarity with the full scope of automation systems is a frequent contributor. Finally, we noticed that accidents related to automation typically stem from surprises, of which there are two types: situational and fundamental. Situational surprises are typical and have known solutions, while fundamental surprises are atypical and have no known solutions, which makes them the more dangerous of the two types.
From our accident case studies, a number of recommendations can be made with respect to automation design, its implementation, and how pilots interact with it. Beginning with automation design, these systems should be robust such that they can operate with various perturbations and abnormal flight conditions without failing. The cases involving flight controls, such as the 737 MAX and Air France 296 crashes, were a result of flight control automation malfunctions when put into a non-standard configuration. Widening the operating margins or increasing the pilot's authority in these systems will likely increase overall reliability, which was a shortcoming in the cases that we researched. With any change made, regardless of the level of pilot authority or operating capability, the functions and capabilities of any automation system must be documented and properly communicated to the pilots so that any behaviors and nuances can be expected and accounted for by the crew. The particular cases of Asiana Flight 214 and the 737 MAX crashes could possibly have been prevented had the crew known about the aircraft's automation capabilities and shortcomings. Moving on to the cockpit, the avionics interfaces represent the means by which information is exchanged between pilots and aircraft systems. As such, as long as humans remain at the center of cockpit operations, automation must be optimized for human tendencies and behaviors. One possible method is to design automation that is controlled or displayed in the same way as the aircraft is flown without automation, such as manually setting the throttle levers before engaging autothrottle, or having the throttle levers physically move as the autothrottle modulates the thrust setting. Interfaces such as control panels should have distinct functionalities, or, if containing multiple functions, should have clear procedures and indications for their correct operation to mitigate mode error. These solutions will require further research, likely through hands-on testing of different cockpit layouts. There likely exists a balance between quote-unquote all-in-one integrated avionics, such as seen in this Embraer E-Jet here, and one-to-one distinct avionics systems like we have in my old Piper Cherokee over here, concerning the amount of information displayed to a pilot in a given system or display. Different cockpit layouts of avionics should be explored, and technologies such as eye tracking may be useful research tools to determine the pilot's focus and comparative awareness with different avionics layouts. These detailed solutions, however, are beyond the scope of this study and should be explored in addition to the simpler goal of improving pilot training for different modes of automation and designing automation to be more intuitively understood by pilots. We hope that was an informative look at our findings regarding aircraft automation. Our next steps are to conclude any analysis of affected automation subsystems and, of course, to finish and edit the paper. With that, thank you all for watching. Please let us know if you have any questions, and here are our references.